what happens there is that the hydrogen will take that electron, and this hydrogen will take an electron from another sodium. And once we have hydrogen atoms, then those will combine to form H2 gas. And the H2 gas is what caused the explosion, H2 gas and water. Hydrogen gas is a pretty good reducing agent. It's up here, though. Not as good as these, though, but still pretty decent reducing agent. That's compared to sodium ion. Sodium ion is very stable. And so you can sprinkle sodium ions and chloride ions on your food, but you wouldn't put chlorine gas or sodium metal on your food, that's for sure. All right, so that was the part two. So be careful. The sign is very important. And redox reactions typically are much more violent than, or potentially violent than acid-base and metathesis. If you have a strong acid and a strong base, and you do a titration, let's say sodium hydroxide and HCl titration, are you going to worry about the Erlenmeyer flask exploding as you're running your titration? Not at all. I mean, you do these titrations, it's no big deal. Strong acid, strong base. But if you take a strong oxidizer or a strong reducer and mix them together, you have to watch out. You have to be especially careful. And the reason is because of these changes in oxidation state. And this is one of the reasons why I classify reactions in this way. You know, in redox reactions, you're going through tremendous changes in stability, you know, between sodium metal and sodium ion. Sodium ion is stable. Sodium metal is unstable, and there's a huge difference in stability there. Whereas when you're neutralizing an acid or a base, the oxidation states don't change. All you're doing is you're making a little bit stronger bonds or a little bit weaker bonds. Do you guys remember calculating or estimating delta H for reaction by summing up the bond enthalpies of the reactants minus the bond enthalpies of the products? Well, those bond enthalpies, those are small changes. When you're forming a precipitate, you're creating a lattice. Sometimes the lattice isn't quite strong, like in aluminum oxide, but when I bring aluminum ions and oxide ions, I don't expect an explosion. I just expect a strong lattice and a good precipitate. That's it. And so there's a huge difference between, again, acid-base, metathesis, and when compared to redox. All right, so that's that. So this is a very weak oxidizer, but still it can react. Nitrate is a much more powerful oxidizer. However, this is missing something. What's missing? The hydrogen, the acid, missing H+. Sometimes we can get the H+ from different things. So for example, if we add acid to this, that'll give it H+. But there are other ways we can get H+, like this. So if we compare this to ammonium nitrate is completely different than sodium nitrate in terms of properties. When we think about ammonium nitrate, let's compare ammonium with sodium ion over here. Sodium ion was neutral in terms of acid-base properties. Is ammonium ion neutral in terms of acid-base properties? No. What is ammonium? An acid or a base? It's an acid. It's a weak acid, but it's an acid. So let's take a look at that. It's fairly weak acid. So ammonium can provide H+ to this. And so H+ and nitrate, that makes a great combination for a strong oxidizer. But there's one more thing. Sodium ions are an oxidizer. They have no electrons to lose other than the core electrons, and it costs too much energy to ionize the core electrons. What about ammonium? Is ammonium electron poor or electron rich? Now, ammonium doesn't occur on a redox chart, and so we're going to have to try to use some structural analysis to determine what we think about ammonium. Would you consider ammonium electron poor, electron rich? Does ammonium burn? Can you burn like ammonium chloride? Will it burn? What do you think? Yeah? What about sodium chloride? Does sodium chloride burn very well? Or sodium nitrate burn? No. You wouldn't expect it to burn much, but ammonium, yes. Why would ammonium burn? Because ammonium would burn because it's fairly electron rich. But you might say, well, ammonium has a positive charge. How can it be electron rich? Well, it depends on where the positive charge goes. So this nitrate is electron poor. And a lot of people don't think it's electron poor because when you look at nitrate, nitrate has an extra electron. It's NO3 minus. But when we look at the structure of this, then it becomes a little clearer why nitrate. Would be electron poor. And so one of the things we'll do is we'll look at the formal charge. Over here, the formal charge on these oxygens are -1, -1. What's the formal charge on the nitrogen? +1. And the formal charge on this oxygen? This one's actually going to be 0. 1, 2, 3, 4, 5, 6. So it's 0. So does this look electron rich to you? Does it look electron poor to you? Well, we shouldn't use formal charge to determine electron rich or electron poor. We need to use what to determine if it's electron rich or electron poor? Oxidation state. So tell me the oxidation states here. Okay, nitrogen is what? +5. Oxygens? Let's take this top oxygen. What's the top oxygen?
-2.
-2. Winner take all. So that's 2, 4, 6, 8. This bottom oxygen? -2. 2, 4, 6, 8. Winner take all. And this one?
-2.
-2. So that's the same. So when I look at this, oxygen at -2, that's normal. That's like water. You know, is water very flammable? Is it electron rich? Can you burn it? No. And so this is normal for oxygen. And where does that extra electron end up? The extra electron in nitrate ends up on oxygen. So let's go ahead and remove it. If I remove one of these extra electrons off oxygen, like this, and change this to -1, so now this would just be NO3. Does that look okay to you structurally? No. I mean, we're going to lack an octet here. This is what we call a dangling bond. This lone electron wants another electron, either by bonding or by taking it. And that dangling bond, we have a name for these. This is called a free radical. Free radical is quite reactive. And so it's not electron rich. You know, if we put that extra electron back, then we have an octet and oxygen's happy once again. It's happy and stable. So this is going to be -2. And so there's nothing rich about oxygen having a -2. Look at water. Water has oxygen in the -2. What looks unhappy is nitrogen. How many valence electrons does nitrogen have? 5. So nitrogen's lost all 5 of its valence electrons, so now it's isoelectronic with helium. So nitrogen's oxidation state runs from +5 all the way to minus what? So nitrogen can lose 5 electrons to be like helium, or nitrogen can gain how many electrons to be like neon? 3. So nitrogen's oxidation state ranges from +5 to -3. So we're at the limit. This nitrogen can't lose any more electrons. The only thing that this nitrogen can do is to gain electrons, right? And so this is why this is electron poor. For this, what we're going to do is we're going to sum up the oxidation states. So minus 2, minus 2, minus 2 is minus 6 plus 5 gives us a net charge of minus 1. Or we sum up the formal charges. If we sum up the formal charges, minus 1 minus 2 plus 1 is minus 1. So we sum up either to get the net charge. Now let's take a look at ammonium. If I look at ammonium, this one is electron rich. Why is it electron rich? It has a positive charge. Where's that positive charge? That positive charge is on nitrogen. Okay, nitrogen should have 5 electrons, but it only ends up with 4 here. 1, 2, 3, 4 when we count this by a formal charge. And so it's 1 electron short. And so it looks like nitrogen comes out short of electrons, doesn't it? And so who's rich? Well, the hydrogens are all 0. And this whole thing carries a net charge of plus 1. So how is this rich? This is rich because I'm not analyzing it like I should. If I'm trying to analyze redox properties, I should be looking at what? Oxidation states. So what are the oxidation states here? Nitrogen is, well, nitrogen versus hydrogen, who's more electronegative? Which one's closer to fluorine? Fluorine's the most electronegative. Hydrogen is stuck here between boron and carbon. And so nitrogen is closer to fluorine, it's more electronegative. Nitrogen wins all the electrons. So if nitrogen wins all the electrons, then it's going to get 2, 4, 6, 8. How many electrons did it contribute? 5. So it ends up with 3 extra electrons, which means minus 3. So over here, this is as poor as nitrogen can get. Over here, this is as rich as nitrogen can get. And so we see the tail of 2 nitrogens. We see the tail of 2 nitrogens because in ammonium nitrate, one of them is extremely poor, plus 5. The other one is extremely rich at minus 3. That's okay. You know, that could be sustained for a while. So ammonium nitrate's a solid. And so if we have solid ammonium nitrate, it's what we call metastable. You know, it's stable, but for how long? Now, in solids, we have vibrational motion. So the ammoniums are vibrating, the nitrates are vibrating. As the temperature gets hotter and hotter, the vibrations get more intense. And as the vibrations get more intense, and then we got acid present because of ammonium, this could lose a proton, then they can collide with one another. If the ions collide with one another, then they can react. And so if they react, this is what we got. We got a nitrogen and a tug of war with a nitrogen. One nitrogen has no electrons, the other nitrogen has all the electrons. There's 8 electrons difference. And so what's going to happen? Well, what's going to happen is there's going to be a reaction. And so this compound here is inherently unstable, whereas this compound, okay, it's an oxidizer, but it's stable as long as there's nothing it can oxidize, and it can't oxidize sodium ions because those are oxidizers too. And so this is when I look at the chemical properties, I see a huge difference in the chemical properties between these two. Do you see that? Yeah, it's a huge difference. And so ammonium nitrate has been in the news, you know, recently. This one, let's take a look. Redox, remember, redox is much more energetic.
Holy shit. Fuck yeah, video.
Well, actually, this is not the, sorry. I mean, I guess this is the wrong one. This is on mute, but you guys are... Sorry about that.
crude ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products. You can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? 50 years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter. Lane was a young chemist at the Monsanto chemical plant. He remembered seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it and go pretty well. And there were lots of people, about 100, that lined the part of our parking lot near the ship. They came down to watch the fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
You could see bits and pieces of paper bagging going up through the air and away. And our boss thought, and I thought too, that we were witnessing a nitrate fire. But someone had said, it's a drain ship. The drain is on fire.
So, believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
There was a very, very strong sulfur in the air, sulfur fumes.
Kurt Master watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, the Monsanto secretary, was watching from her office window.
And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dock to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster.
The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that launched a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We have another truck up here off the road. They had about 10 or 15 heads, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City.
So, also Beirut, ammonium nitrate, and others. And let's take a look at another compound here. What do you think of this? Ammonium perchlorate. What do you think of that? What kind of stands out to you? Well, is perchlorate on a redox chart? Let's take a look. I know ammonium's not. And so I take a look here, there's no ammonium, there's no perchlorate. So there could be 2 reasons perchlorate's not on the chart. One, it's not very reactive. If it's not very reactive, why bother having it on the chart? Or 2, it's reactive, it's just ran out of the space to put it on there. What do you think? You think it's reactive and they just ran out of space, or it's not very reactive? We don't have to worry about it too much. Ran out of space? Yeah. What do you think about the redox properties of perchlorate, would you say that's going to be a electron-rich species or electron-poor species? Well, we can't tell by the net charge. The net charge is just the sum of all the charges in the structure. And so this net charge doesn't tell us anything. We have to look at the individual charges on each atom. The individual charges on each atom. So there are two ways of doing that. One is we'll just draw out the Lewis structure. We'll just do perchlorate with all an octet here. Sometimes you'll see perchlorate with an octet like this. Sometimes you'll see perchlorate with an expanded octet. The reason why they want to expand the octet is because of the formal charges. When we look at the formal charges on perchlorate, the formal charges are going to be minus on each of these oxygens, and what on chlorine? What would the formal charge on chlorine be? +3. Chlorine ends up with 1, 2, 3, 4. It should have 7, so it's missing three electrons. So that's what gives it this +3 charge. What some people do is they'll expand the octet to lower the formal charges. And so sometimes what you'll see for perchlorate is a structure that looks like this. Some people will try to totally minimize the formal charge by expanding the octet significantly. Like that. And so what are the formal charges now?
Negative on the single bonding oxygen.
Yeah, negative on this oxygen. How about the other oxygens? The other oxygens, well, let's count it. 1, 2, 3, 4, 5, 6. It gave 6, it got 6. It's good. 0. How about this chlorine? 1, 2, 3, 4, 5, 6, 7. You know, half the bonding electrons. How many did it give? Chlorine has 7 valence electrons. It ends up with 7. And so this is a case where we've expanded the octet and we've minimized the formal charge. Why didn't we do that over here? Because if I expand the octet, I could get rid of the formal charges on this nitrogen and one of the oxygens. So let's say I take an electron pair and donate it to the bond here. That's like donating an electron to nitrogen. It's going to get rid of that formal charge on the nitrogen. And so if I made one more double bond here, I end up with this structure. And this structure will have a negative formal charge on this oxygen, but these two oxygens will be 0 and the nitrogen will be 0. So this looks good, right? There's only one formal charge on this oxygen. So that looks pretty good, except for what?
Violence octet.
Yeah, and for nitrogen, it's not a rule, it's a law, right? For the second period elements, it's a law. You never go over an octet for the second period. And so this is never going to happen, and you'll never see this structure because it's totally wrong. However, if you go to Wikipedia, you'll see this structure. But did I talk about this? What's the current thinking on expanded octets? Yeah, the current thinking at the end of chapter whatever it was, chapter 10 or chapter 9, and I think I mentioned this before, is that it's an octet law for everything. That is no expanded octets. And so how do you get away with having no expanded? Well, this is one way you get away with it, just keep an octet. Now, but what if you have more than 4 things bonded? Then if you have more than 4 things bonded, then 4 of them must be covalently bonded, and the rest must be ionically bonded. So that's one way we can get rid of it. And so for us, we're not going to expand the octet right now because the quantum mechanical calculations are showing that this. And this has ionic interactions here. So we have the covalent interaction here. The ionic interaction would occur between the +3 chlorine and the -1 oxygen. And so there would be electrostatic attraction here, a Coulombic attraction that holds it together in addition to the covalent bond as well. Okay, so we end up with this structure. But the formal charges are very useful for us to determine things like acid-base properties sometimes and the lowest energy Lewis structure. But for redox properties, we want to look at what? Yeah, the oxidation states. So tell me what the oxidation states are on the oxygens. All the oxygens are the same stuff. -2. What's the oxidation state on chlorine? +7. So what would you consider this? Would you consider this electron rich or electron poor or somewhere in between? Electron poor. And in fact, +7 is, what does the oxidation state for chlorine run from? Chlorine runs from +7, which would make it isoelectronic with neon, to -1. So that would be the range of oxidation states. So this is maxed out. You can't oxidize this anymore. Perchlorate is the max. And so, so that makes it electron poor. And that +7 is significant. This is a significant oxidizer here. And so let's take a look at how perchlorate reacts.
You're about to see some of the most astounding moments of the Emerson, Nevada, a chemical fire has ignited at the rocket fuel manufacturing plant, Chem. It's hurt with every second that passes, the fire grows. What they don't know is that the inferno now threatens a storage area. 6 million pounds of the rocket fuel is down. If the chemicals exceed 716 degrees Fahrenheit, the entire area will combust. Then, unforgettable. As the explosion erupts, a powerful shockwave careens across the landscape, and a car traveling along an adjacent highway is caught in the blast. Multicolored smoke indicates that bombs and chemicals continue to burn, leading one to question, did the blast detonate all of the rocket fuel inside the plant? The explosion is massive. Its shockwave completely decimates this building. The blast is so strong, it registers an earthquake measuring 3.5 on the Richter scale, 600 miles away. Two people were killed in the massive explosion. What you are looking at is $100 million worth of destruction. These skeletal remains used to be a chemical manufacturing plant that produced rocket fuel for the space shuttle.
All right, so perchlorate isn't on the list, but it's pretty violent, isn't it? And so it's a very powerful oxidizer, perchlorate. And that's what they had at the FEFCOM plant there. This is a perchlorate plant. Problem with perchlorate is it doesn't have very good metathesis properties. You know, so it turns out the water in Nevada is contaminated with perchlorate salts. So one of the things they tried to do is they tried to precipitate out the perchlorate, but there's nothing to precipitate out the perchlorate with. And so it turned out to be a huge challenge to clean the groundwater perchlorate. But they finally did it. They figured some way of getting the perchlorate levels to acceptable levels for the drinking water in Nevada. And so they had a big celebration. It was maybe 10 years ago or 15 years ago where they showed people drinking the tap water. Before there was lots of perchlorate in the water. And now it's much better. Okay. All right, let's see. Let's go on. We're going till what time? 5:35. Okay, we'll take a look at some more redox chemistry here, and then we're going to talk about Lewis acid base reactions. So sometimes you want to dissolve metals. Like, for example, sometimes you want to dissolve copper. No. If you wanted to dissolve copper, you can't use hydrochloric acid. It's not enough. Or any mineral acid. You need an oxidizing acid. So nitric acid will dissolve copper metal. But will nitric acid dissolve gold metal? And so it depends on where gold is. So if we look at gold, how can we dissolve gold? You aren't going to be able to dissolve this chemically, but physically, but you can dissolve it chemically. And so when we look at where gold lies, then let me show you. In the back of our book, we have a more comprehensive redox chart. But I'm still not able to access our e-text book. And so rather than show you that, we'll look at some gold. Reactions here. So this is just like our chart. Over on the left are the oxidizing agents, over on the right are the reducing agents. Ignore this last one here, the gold and the chloride. Well, if we look at gold, the strongest reducing agents is gold going to gold 3 plus here. And so where do we place that? Well, this is at 1.52 volts. So if I tried to dissolve gold, what would I need to dissolve it? So that's at 1.52 volts. Go back to this. And so just like what we did with water, we're going to do that with gold. And so gold going to gold 3 is at 1.52 volts, which pushes it between here. And so here would be gold metal. And then here would be gold 3 ion. So gold 3 ion is a powerful oxidizer, but gold metal is a very poor reducing agent. And so what do you need to dissolve gold if it's here? If gold is here, then you can dissolve it with hydrogen peroxide. But this is not household hydrogen peroxide. Household hydrogen peroxide is 3%. You could dissolve it with ozone. You could dissolve it with fluorine. Well, fluorine's very nasty to work with. Ozone, the same thing. Hydrogen peroxide, this is the concentrated stuff that I talked about earlier, which is kind of dangerous. And so, but could you dissolve it with nitric acid? No, you can't dissolve gold with nitric acid. But it turns out that you can dissolve gold with nitric acid and a little bit of help. And so if you have some nitric acid and you add some hydrochloric acid to this, in a 1-to-3 ratio, then you're able to dissolve gold. And so how does this work? Well, the first thing is, this is called aqua regia here. Aqua regia is a raw water. And it's a 1-to-3 mixture of nitric acid and hydrochloric acid. But the funny thing is neither of these act as an acid. And if you look at their chemical roles, this is it. Aqua regia, the nitric acid, is not acting as a strong acid. This is acting as an oxidizer. But there's no way that this is strong enough to oxidize gold. And so this is like somebody who's trying to pedal up a very steep hill. You know, there's no way this person's going to make it. But then somebody else comes along and helps pull that person up the hill. And that somebody else that comes up to help pull it over the hill is hydrochloric acid. And so in order for nitric acid to oxidize gold, gold-3, it's quite an uphill battle. Here. So here we have nitric acid here. And then up here at 1.52, we have gold. And so this is quite an uphill battle to oxidize the gold to form gold-3. And that's not going to happen because of the driving force. So what's going to happen is somebody else is going to pull it along. Who's that somebody else? The somebody else is hydrochloric acid. And the funny thing is this. Hydrochloric acid is an acid, and everybody thinks that hydrochloric acid is an acid. It's a strong acid. But do you ever consider hydrochloric acid as a base? No, you'd never consider hydrochloric acid as a base because chloride is worthless as a base. It's neutral. And so you can't neutralize anything with chloride. However, that's if we only look at it as a Bronsted base. If we look at it as a Lewis base, then chloride is a okay Lewis base. And so hydrochloric acid is not being used as an acid, it's being used as a base. And we would never think of it as a base unless we're looking at it as a Lewis base. And so what is the Lewis base part of hydrochloric acid? It turns out that chloride is a terrible, terrible Bronsted base, but an okay, not great, but okay Lewis base. And that's what's going to help this reaction get over the hump. And so let's look at this reaction in more detail. What I'm going to do is I'm just going to copy these reactions off the chart here. And so for nitric acid, we have nitrate plus 4H plus 3 electrons goes to NO plus 2H2O. For gold, we're going to go from gold to gold-3. And so what I'm going to do is I'm going to put those two together and see what we get. So this is the gold to the gold-3, but I'll go reverse that. Gold is a reactant over here, not a product. So what I'm going to do is I'm going to take this half reaction, what I call half reaction, flip it the other way, and then put those together. So essentially what I want to do is I want to oxidize the gold. And so I'm going to take my gold metal and oxidize it to gold-3 ions plus 3 electrons. So gold doesn't want to lose those electrons, and so we need a very powerful oxidizer to do that. Well, nitric acid is not powerful enough, but let's try it. So if I use nitric acid, it's nitrate plus 4H plus. And so I have plenty of H plus here. I have H plus from the nitric acid, and I have H plus from the HCl. But H plus isn't being used in the redox, plus, other than making water. Plus 3 electrons yields NO. NO is a colorless gas. NO, when it comes into contact with air, it gets oxidized spontaneously to NO2. NO2 has a beautiful orange color. It has a sulfury smell to it. And so it's very characteristic. It's a choking odor. This is like photochemical smog. And then 2 waters. So this is a terrible uphill battle. So if I try to do this with nitric acid, it doesn't really work. And so I get gold plus nitrate. The 3 electrons here that are consumed are from the gold, which produces 3 electrons, plus 4H plus yields gold 3 plus NO plus 2H2O liquid. Now, when I think about motion and kinetic energy, I think about the Maxwell-Boltzmann distribution or the kinetic energy distribution. Do you guys remember the kinetic energy distribution or the speed distribution for ideal gases? Do you remember that? That is, at a given temperature, there is a distribution of energies. So let's say this is room temperature. Even at room temperature, we could have a small population. This is population on the y-axis. So population versus energy. This would be at room temperature, RT. So even at room temperature, there's a very small very small population of high energy molecules. These high energy molecules can undergo violent collisions. And so once in a while, this will happen, goal 3. So there's a violent reaction and it can make it up the hill. But let's say it makes it partway up the hill, then it rolls back down. So we need something to help pull it up the hill. And so this is not enough. This is too big of a hill to climb. And there's just not enough of these high energy species to accomplish it. And so what's going to happen is if gold 3 is formed, then the chloride in HCl is going to attack it. And so gold 3 ion gets attacked by 4 chlorides, like this. And so what's going on there is if I have a gold 3 and a chloride, gold 3 is positively charged, chloride is negatively charged. And so normally we'll have some kind of attraction there, maybe make an ionic bond. But in this case, the attraction is going to be like this. We're going to take the lone pair here, and it's going to donate to the gold 3. When we have a lone pair being donated, it's called a Lewis base. When we have a lone pair being accepted, that's a Lewis acid. So this turns out to be a Lewis acid-base reaction. So the gold 3 is the Lewis acid. The chloride is the Lewis base. And what results is something called a coordinate covalent bond. This bond is quite stable, so we'll have a gold chlorine bond like this. Gold retains its charge at 3+. Chlorine retains its charge at -1. Now, this bond here is called a coordinate covalent or dative bond. Okay, once we form one of these, then there's room for 3 more. And so altogether 4 chlorides will attack the gold. When that happens, we form this. It's going to be AuCl4. This whole thing is going to carry a net charge of -1. +3 minus 4 gives us -1. And the name of this is called tetrachloroaurate. Roman numeral 3 ion. This is all one word here. The structure of the tetrachloroaurate ion looks like this. It's going to have 4 covalent bonds in a square planar arrangement, like this. And these 4 chlorines are going to be covalently bonded, not ionically bonded, to the metal. So usually when we have a metal and non-metal, we form ionic bonds. In this case, we're going to form covalent bonds here. And these bonds are called, again, coordinate covalent or dative bonds. And this whole thing is going to carry a charge of -1. And so we add up out of the individual charges. Now, when we add up the individual charges, the chlorines retain their charge of -1, the gold is +3. And so -1, -2, -3, -4, +3. This is different than the way we've been counting things now, up to now. And it turns out even this shape is square planar, and it doesn't make sense according to valence bond theory and Vesper. And so it turns out that valence bond theory fails for these types of species. And we have to use MO. Must use MO. Molecular orbital theory. But this is what we call a complex ion. Not everything forms complex ions. So, for example, gold is a pretty good Lewis acid, but sodium ions aren't. And so, you can look at some other ions. So, for example, if I have a sodium ion, the water is not going to form coordinate covalent bonds. In other words, if I have sodium ions, what I'm going to get is a hydration or a solvation sphere. And I'll generate these, what we call ion dipole attractions. So there's going to be an ion dipole attraction here. And then I can fit about 6 of the water molecules around this. But this is not bonded. However, if I have aluminum 3+, and a water comes along, that water is going to actually bond to the aluminum here. And so what we say is sodium ion is a very poor Lewis acid. It's a poor Lewis acid, it's a poor electron pair acceptor. Sodium ions, low charge, big size. Aluminum ions are good Lewis acid. Small size, high charge. And that interaction becomes pretty intense such that the lone pair can actually bond to the aluminum like this and form a coordinate covalent or dated bond here. We can fit 6 water molecules around this in an octahedral arrangement. Where the oxygens attach to this. There's going to be a large inductive effect. This large inductive effect makes these hydrogens much more acidic than in normal water. The large inductive effect is because of all the positive charge concentrated here, sucking in the electron cloud here. So it turns out that since these hydrogens become much more acidic than in normal water, this complex ion, which we call, is it 4 waters? Actually, it should be 4 water. Could be 6 stuff too. We would call that, one of the chemical properties of that would be it's a Bronsted acid. So when we go back to the acid chart, let's take a look at that. When we look at the acid chart, we see this funny species here. Did you notice this one? This is a funny species. This is a complex ion. It's iron 3. Iron 3 is a good Lewis acid. Water is a Lewis base. And the waters actually bond to the iron by a covalent bond like the aluminum did over there. And once the water is bonded to it, there's a large inductive effect making these hydrogens much more acidic. In fact, if you look at the acidity of these hydrogens on the waters that are bonded to iron, this is more acidic than nitrous acid. This is more acidic than hydrofluoric acid. What is this? The name of this is hexa-aqua iron 3 ion. And this is an example of a complex. So we're going to be looking at complexes in the next section, which is chapter 24. One of the complexes that well, actually, I forgot to finish this one. But anyway, what's happening here is the formation of this complex is quite stable, and so this pulls it along. So even though this initial redox reaction wasn't favored at all, by coupling these two reactions, that is, by having this second reaction here, which is the Lewis acid-base reaction, it'll help pull this up that steep hill, because this is such a favorable reaction here. Okay, one of the complexes that we were looking at earlier, and this one is kind of big, is this, EDTA. EDTA is called a chelating agent / complexing agent. And so EDTA is an excellent Lewis base. EDTA actually has a 4- charge. And so we're going to draw this one out here. This EDTA equals ethylene, diamine, tetraacetatum, or let's call it acetate. Ethylene diamine tetraacetate ion. And it consists of an ethylene group. F stands for 2 carbons. And so ethylene would be a CH2CH2. And then it's going to have 2 amines. Amines are like ammonia, like derivatives. So let's take a look at amines real quick over here. If we look at ammonia, ammonia is a base. And it's also a very, very, very weak acid. But normally when people think of ammonia, they think base. What makes ammonia a good base? Ammonia is a good base because it can accept a proton. It accepts a proton here to this lone pair. So if a proton comes in, we can form ammonium by converting this lone pair into bonding pair. It's also a Lewis base because it has a lone pair that can be donated. When we look at this, though, we look at the polarity. The polarity is going to result in net negative charge on the nitrogen. Nitrogen is more electronegative than hydrogen. So the bonding electrons here are polarized towards nitrogen, all of them. So we have this, this, and this. So we're going to get negative charge buildup on the nitrogen here. Well, amines are ammonia-like bases. And so if we take that hydrogen and replace it with a carbon group, like CH3, CH3 is called methyl, we end up with methylamine. Methylamine is going to have very similar base properties to ammonia because hydrogen versus carbon, carbon has electronegativity 2.5, hydrogen has electronegativity 2.1. The difference between a 2.5 and a 2.1 is small, negligible. So they have comparable electronegativities. If they have comparable electronegativities, then what that means is the polarization of the electron cloud is going to be roughly the same. Just a little bit less because carbon is a little bit more electronegative than hydrogen, but very comparable. And so the delta minus here is going to be almost the same as this. And so both of these are Bronsted bases, both of these are Lewis bases. And so we could replace all the hydrogens with carbon and it doesn't change the base properties of ammonia much at all. And so in ethylene diamine, we're going to have 2 amines. The 2 amines are stuck here. There's one here and one here. Now, there's going to be no hydrogens bonded to the nitrogen here because what we're going to do is we're going to bond 4 acetates to this. And so here, nitrogen is going to have 3 bonds, and then we're going to have a lone pair like this, and we'll put in an acetate here. Normally, acetate would start off with CH3, but we have a bond here to the nitrogen, so it's going to be CH2, and then we're going to have a double bonded O. This is a CO, and then an OH, so COOH. COOH is the carboxyl group, or the carboxylic acid group here. And so it's like acetic acid, except there's no H here, sorry. This is going to be COO minus, and so this will be acetate rather than acetic acid. And so the same thing goes down here. We're going to have a CH2, C, double bond O, O with a negative charge here. So that's 2 acetate groups. Now we're going to have a third acetate group here, CH2, C double bond O, O minus. 3 acetate groups, and then the 4th acetate group we'll put down here, CH2, CO, O minus. So this is the ethylene diamine tetraacetate ion, or EDTA. Now EDTA loves to attack Lewis acids. So if there's gold ion around, EDTA will attack that and completely encapsulate it. And so let's take a look at one. Let's take a look at lead. Did I talk about lead poisoning? Did we look at the CDC thing on lead, the 2-year-old? No, we didn't. Okay. EDTA is what we call a chelating agent. It loves Lewis acids. Lewis acids are like those metal ions, like lead-2 ions. And so EDTA is proposed as a medication for lead poisoning. We'll just finish up with this. All right, so there are 2 medications given for lead poisoning. One is calcium EDTA, the other is sodium EDTA. And what the EDTA does is it seeks out lead and then bonds to it, coordinate covalent bonds, dative bonds. And so here, these 2 medications, one's more aggressive, the other's less aggressive. Which one would be more aggressive? Sodium EDTA or calcium EDTA? Sodium EDTA, that's correct. Sodium EDTA would be more aggressive because? Why? I'm sorry? Sodium versus calcium? It has to do with the charge. The charge. Think about which one's more aggressive. If you're going to clean your drain, could you use, let's say you ran out of drain cleaner, but you have milk of magnesia. Did I talk about the milk of magnesia? You ran out of drain cleaner, but you have milk of magnesia. So you're going to dump a whole bunch of milk of magnesia, although it'd be expensive, down your sink. Is that going to be very effective? It's not going to be effective at all. Why? Because you need the hydroxide free to attack, the hydroxide. If there's fats in the drain clogging it, the hydroxides will hydrolyze those fats, fatty acids, or whatever else, hair, other things. And so it's not going to be effective because the hydroxides are locked in the lattice. Well, EDTA needs to be free. EDTA needs to be free to find lead ions. When it finds a lead ion, then it's going to encapsulate it. It's a chelating just means cloth. Chelating complexing agent. And so which of these 2 are going to have more EDTA that's free to react? The calcium or the sodium? The sodium, because it's a weaker ionic bond here. With calcium, it's a stronger bond to the EDTA. Does that make sense? So it makes it less reactive. In other words, the EDTA is going to be hindered by the calcium. So in other words, the sodium EDTA is there for acute cases, but the calcium EDTA is there for most cases. So according to the package insert, Sodium EDTA is indicated for selected patients for the emergency treatment of hypercalcemia and for the control of ventricular arrhythmias. So EDTA, hypercalcemia is too much calcium. So EDTA can capture the calcium and lower your calcium levels too. But it can also capture lead. EDTA, the sodium EDTA is not meant for children though. So I just covered it. The only agent recommended for intravenous chelation therapy in children is calcium EDTA, which makes sense. It's less aggressive. All right, so let's take a look at the case report. Texas. In February 2005, a girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary blood lead level, BLL, of 47 micrograms per deciliter. A venous blood lead level of 48 micrograms per deciliter obtained 12 days later confirmed the elevated blood lead levels, BLLs. A complete blood count and iron study conducted concurrently revealed low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. The patient's blood electrolytes at admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral Suxamar. The medication order was subsequently corrected by the pediatric resident to intravenous calcium EDTA. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2. Milligrams per deciliter. Normal is 8.5 to 10.5. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values of serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 5 milligrams per deciliter despite repeated doses of calcium chloride. All attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. So in 4 p.m., dead by 8:12 a.m. the next day is pretty tragic. And that's like this is the drain cleaner. The drain cleaner version, you're giving it to the child, the sodium EDTA, versus the milk of magnesia version. And so unfortunately